Right, we have a different type of induction proof here. It's an inequality proof. I have seen these come up in exam papers, so they certainly, you need to learn them. It's a kind of a different feel to how you solve it, but I think once you get the hang of it, and hopefully you remember it and practice enough, then you'll know what to do if and when you do see one of these. So we need to prove that 3 to the n is less than n factorial for all integers n, where n is greater than 6, right? So 7, 8, 9, 10, and so on. Right, we're going to prove this by the principle of mathematical induction. Start in the usual way, so we need to say what we're trying to prove. So the proposition we're trying to prove is that 3 to the n is less than n factorial for all integer n where n is greater than 6, 7 or more. Right, so that's what we're trying to prove, and then we need to say proof, and we need to say that we're doing it by the principle of mathematical induction. So proof by the principle of mathematical induction. Okay, so we're going to need our basis step when we start with a basic number. You need to think about what you're using. It's certainly not 0, it's certainly not 1. The lowest possible number n can be is 7. N needs to be an integer, it needs to be greater than 6. So if n equals 7, so we need to show that 3 to the 7 is less than 7 factorial. Now this would obviously, now you know, this would come up in a calculator paper 2. I'm not going to bother showing you the calculation, I'm sure you can do that. But 3 to the power 7 is 2187, and 7 factorial is 5040. So clearly this shows that P proposition is true when n is 7. So P7 is true. Right, so the second step, we assume that the kth case is true. So if pk is true, then 3 to the k is less than k factorial. Okay, so we're good so far. Now it kind of takes on a different feel. So we're looking, you might think about a target. So we have a target in mind. What we want to show is this, but n is replaced by k plus 1. So we want to show that 3 to the power k plus 1 is less than k plus 1 factorial. And we can't sort of form this k plus 1th case in the normal way. When we're dealing with, say, a sequence or a series, we'll kind of build towards k plus 1, and then we'll use the result to simplify it. Here, the only thing we've got to work with is the kth case. So we're now looking to use this to prove that this is true. And we're going to go straight from here. This 3 to the k plus 1 is 3 times 3 to the k. So I can make this, say, 3 to the k plus 1 if I multiply it by 3. If I'm going to do that and keep the same inequality, I need to multiply both sides by 3. Obviously 3 is a positive number, so I don't need to flip the inequality when I do that. So that would be 3 times 3 to the k is less than 3 times k factorial. K plus 1 factorial means k plus 1 times k minus 1 times k minus 2 times k minus 3, all the way down to 3 times 2 times 1. So k plus 1 factorial, again, this is another simplification that you need to be very good at, is it's k plus 1 times k factorial. I'll write that down in a minute. What do we know about k? Well, we know from here that k is greater than 6, right? So if k is greater than 6, well, k is definitely greater than 3, and so is k plus 1. K plus 1 is definitely greater than 3 if k is greater than 6, right? So if we have k plus 1 is greater than 3, which we know to be true, if we multiply both sides by k factorial, which we know is definitely positive, then we're going to get this. So if we times both sides by k factorial, that would say k plus 1 times k factorial is greater than 3 times k factorial, right? Now, as I was saying earlier, k plus 1 times k factorial is k plus 1 factorial, because it's k plus 1 times k minus 1 times k minus 2 times k minus 3, all the way down to 3 times 2 times 1. So this is k plus 1 factorial, which is greater than 3 times k factorial, right? This is interesting. So if we go back to our inequality we've got here, this one, we know that 3 times 3 to the k is less than 3 times k factorial. But 3 times k factorial is less than k plus 1 factorial. Okay, so that must mean now that k plus 1 factorial is greater than 3 times 3 to the k. We know that 3 times 3 to the k is 3 to the k plus 1. 3 to the k plus 1 must be less than k plus 1 factorial. And that is what our target is. So we've now shown this is complicated, but it is always the same for this type of thing. So now we can wrap it up. So since P7 is true, as was shown in step 1, and pk plus 1 is true whenever pk is true, so since those things are both the case, Pn is true for all integer n where n is greater than 6. And that is because of the principle of mathematical induction.